let's have a look. So the next one we're going to do is nitration of an aromatic ring. So we're going to add a nitro group. So to start this, we need nitric acid and sulfuric acid. Okay. So nitric acid looks a bit like that, okay? And sulfuric acid, we don't need to worry about the structure of the sulfuric acid, it's just there to provide H+. Okay? And what we're going to do is we're going to add that H+. And what you'll see most of the time when I put charges in, I put circles around them. Okay, now it just really highlights that there's a charge there. If you just put a little plus or a little minus, sometimes you completely miss it. So make sure it's absolutely clear. So what we've done here is we've taken some other acid, okay? So the sulfuric acid, oh, where's it gone? There it is. So we've taken the sulfuric acid and we've protonated the nitric acid. So we've added a proton to the OH group. This is an equilibrium. It could be that it would add to where the O- is. Okay, but if it did that, that wouldn't give us the mechanism that we need or the structure that we need to continue the mechanism. And you can see this is all in equilibrium. So all we're saying is at some point, this will happen. And once this happens, what we can then do is we can lose water. And what it gives us is a nitronium ion. And that's all this is showing you. So again, what I need you to understand is if you see nitric acid and sulfuric acid together, that's going to give you NO2+. And this is what the structure of NO2+ looks like. If you can show me how that happens, great. You might get an extra mark, okay, out of a 5-mark question. But as long as you can recognise that it gives you NO2+, that is the absolute key thing. And then that's just our electrophile. That's just the thing that we're going to then use to make our aromatic ring to do our substitution reaction. So we just need to create the NO2+, and then the next step is we're going to add that to our aromatic ring. So that will look like this. So we have our ring, and we have our NO2+, okay? And I'm not worrying about showing you all the other stuff now. We can just treat it as NO2+. And so that's our E+, it's our electrophile, so we do exactly the same mechanism that we've done twice now. One is a general mechanism, one is adding the chloride. We take the electrons out of the ring, we add it to the electrophile. Now, the nitrogen needs to do something because it would have too many bonds. But that's quite easy because we can just take some electrons from a nitrogen-oxygen bond. And we can add our positive charge. So that is the same mechanism of just the general electrophilic substitution. We've just added the nitrogen group, and because of that, we just have that extra arrow in there to say, the nitrogen would have too many bonds now if we take one of them away. And if we're going to take a bond away, we're always going to take a pi bond. We're going to break that double bond before we break any kind of single bonds. And then again, you have your hydrogen, and we would just lose the hydrogen. Keep drawing my angle wrong there. Okay, so we just add our nitro group. So same mechanism. We can drill the same resonance structures. Again, I recommend that when you're doing, looking back at this, have a go at drawing them out. Okay, because it's really important to understand what we mean by resonance, how we move that charge and change the electron density within the ring. So we've added the nitro group again. Okay. We can do the same with sulfonation. The reason I'm showing you these three is these are ones that you will often see in drug molecules. You will see sulfonyl groups. They're really handy for things like solubility. Okay. This, again, I'm not too worried. That's why I'm not going through it in detail. All I want you to realise is that if, again, you see sulfuric acid, you can, within sulfuric acid, you have sulfur trioxide. So that is the structure down at the bottom here. Okay. So you've got this. If you see sulfuric acid, the electrophile you're going to use is actually sulfur trioxide. And what we can see in this resonance structure is we're saying, well, look, the sulfur has a positive charge. And that's the key thing. So that sulfur has that positive charge. Okay. All you need to take away from this slide. See sulfuric acid, know that sulfur trioxide is present. Okay, so then we would do the same reaction that we've done before. So we've got our ring, and this time we have our electrophile. So it's a bit like the nitro one, except this time it's sulfur and it's got 3 oxygens double bonded to it. But we do exactly the same process. We take the electrons out of the ring. Okay. The sulfur again would then have too many bonds. So we can break one of those sulfur oxygen double bonds. Okay, so it's exactly the same as we've done before, and then we've got our hydrogen that sits there. We can take that out. Okay, yes. Yes, so it's forming the bond between there, yeah. And then at the end of this, you can add H plus. To form your benzyne sulfonic acid, it's called, benzene sulfonic acid. But the principle that you need to understand is that the mechanism is exactly the same. So I've shown you now 3 additions. So chlorine, you did bromine, we've done the nitro, and we've done the sulfonyl. Okay, but the underlying mechanism, that addition or that substitution, is exactly the same. All we're doing is understanding how do we get our electrophile. And once you've got your electrophile, then you're following the same procedure, the same mechanism, the same movement of electrons. So out of the ring towards the electrophile. Once the electrophile's been added, we can show this resonance stabilization. And then finally we can show, well, we remove the hydrogen and we reform the aromatic ring and we get substitution. Let's have a look. So the next one we're going to do is nitration.